All right, thank you, Jeff. So we're going to talk about, like Jeff said, fine lightweight aggregate, saturated fine lightweight aggregate, and measuring electrical resistivity of materials made with that. And this is work done by myself and my current PhD student, Eleanor Skelton. She has a PE because she was working in industry for a number of years and decided she wanted to come back, take a huge pay cut, learn some more stuff, and do some exciting research. So happy to have her on board. And what we're going to talk about today is just a thought I had as I was, looking through some of the old resistivity data over the past decades and thinking about, well, if we were measuring resistivity on a, internally cured, let's say, bridge deck, wouldn't the high porosity of the lightweight aggregate, somehow affect the resistivity readings? Not necessarily make it worse or better, because that's not really a good way to describe it, but the porosity inside the aggregate itself should, in theory, affect the resistivity readings. And so went to literature, found that, okay, some people have measured resistivity of internally cured mixtures. The first reference there, Wang and Tran, they only looked at lightweight aggregate mixtures, so they didn't really have a comparison to just normal concrete. De la Varga looked at surface resistivity readings, which is very appropriate for like a bridge deck kind of evaluation. DiBella, in both of those publications, looked at internally cured field mixtures, but they had been saturated, so they had been sitting in a lime bath their entire life, if you will. And so we had kind of the pieces of this in terms of mixtures and internally curing and resistivity readings, but nothing kind of tying it together to see, okay, what is there an effect? Because if we look at some of these publications, we see that in some cases, through just resistivity readings, we see that there is no difference in the resistivity reading between an internally cured mixture and its companion normal weight mixture or non-internally cured. And then in other cases, we see a significant difference. And so that's kind of what got me thinking about this. So developed a testing plan where we're looking at various water cement ratios, different saturated fine lightweight content percentages, and then both looking at mortar and concrete mixtures. And when we do the design, all the designs are remaining volumetrically the same so that we can actually evaluate the effect more consistently. And we were looking at sealed curing to see, all right, if we have kind of a representative structure, what are we looking at? And then at the end of that 28 days of sealed curing, we'll go ahead and oven dry it. We'll actually take a resistivity measurement of the oven dry sample. Our impedance analyzers can actually measure this, although it's not really that useful. It's just kind of a neat thing to do. But most importantly, after we oven dry, we'll vacuum saturate it and then take a final resistivity reading. And so we did this with several pieces of equipment. We have a commercially available concrete resistivity device. We have several impedance analyzers available in our lab. We have an older HP 4194A impedance analyzer, and then a much more modern Keysight E4990A impedance analyzer. And we're in the process of acquiring a Solartron impedance analyzer to kind of round out this part of the study. And we also have a vacuum saturation chamber so that we can ensure we get all of our mixes into what we would hope is a near 100% saturated state for that final reading. We had the best intentions with all this. And then, of course, 2020 happened. And in fact, we actually had most of the mixes cast. And 2 days after that, the university shut down. Okay, well, all right, we shut down for a little while. And then in the summer, we're hoping to get back into the lab. Turns out they're only going to start, access to the lab with externally funded projects. This happened to be an internally funded project, so we got pushed off to August 1st. as the first day we could go back into the lab and start our study. So obviously the specimens we cast way back at the start of March were no longer good because they had aged out. So we essentially restarted the study. I don't have a lot of data, but I do have some data that we can talk about. And we actually discovered something completely unrelated to all of this during the course of this study that's actually going to take us in another direction, along with looking at lightweight aggregate and resistivity. All right, so some of the data we have. If we look at a Bode plot, we have frequency of our signal on the x-axis, and we have impedance on the y-axis. And we have our different mixtures, our 0, 25, 50, 100% lightweight. These are all in saturated state when they're added to the mix. And we look at 1 day after casting, and we kind of see what is reasonably expected. And we'll talk about these spurious measurements right here later in the presentation. That's what I was mentioning when I said we discovered something completely off track, if you will, of this. So we got that at 1 day. We go to 3 day, and the scale of the y-axis will remain the same for all these graphs. And you see the resistivity increases overall, which is kind of expected, where our 100% lightweight is significantly down here. And all of this data is actually an average of 5 samples for each mix. And so you can see in the case here, you have error bars, and we have rather consistent measurements. Then we get to our 28 days sealed. Again, resistivity increases, and we have, our non-internally cured mix with the highest impedance, the I guess you could call it moderately internally cured mixtures here, and then 100% lightweight down here. And then we vacuum saturate it. We oven dry and then vacuum saturate, and we see something very interesting happen. And we look at 28 days sealed, and then we oven dry and then vacuum saturate. It's not necessarily the issue of the impedance value. Like, we expect it to go down a little bit because we're going to saturate it in a representative pore solution that's calculated using the NIST pore solution calculator. But what's more striking is the almost the order in which the values change. So at the sealed state at 28 days, we see that, all right, we have the highest impedance at, non-internally cured mixture, then the lowest with the internally cured. But then that kind of switches after we dry it and then resaturate it out. And what's most striking about this is this suggests that if we go out to, let's say, a bridge deck that maybe has not seen a lot of rain, and we take our measurement, and then we are trying to compare that to a measurement we've taken in the lab where we had our specimens lime water saturated the entire time, we may get very different answers. And when we start thinking about performance engineered mixtures and looking at PP84, and we're specifically looking at resistivity measurements, all right, so we have some guidance on how to do these measurements and what we're looking for. And it mentions, a saturated formation factor value. And when we look a little further, we see, all right, most of the PP84 documentation is assuming fully saturated. But however, recent work, not mine, others, has suggested that maybe a sealed formation factor has some merit, and maybe we should consider this for future specifications. Now, we have understood through, again, previous research that we're not going to have a match between a sealed formation factor resistivity reading and a saturated formation factor reading. We know that already. It's been shown a lot with normal weight concrete, and very, very, very little, but there's a few out there with internally cured concrete. And so, we look at the actual test, that bulk resistivity test, the Uniaxial test, TP119, and just look at the scope of this. And, it's talking about is applicable to types of concrete where correlations have been established, using long-term chloride ponding procedures or some other, way to establish a correlation between the resistivity and chloride values. And it gives several publications, and there's others out there to view. And so that brings us back to, okay, well, we have a vacuum saturated condition. We need to almost reconcile these, because if our guidance in PP84 says, well, we're going to assume saturated, but, sealed is also, has merit, and, we're kind of dealing with two different mechanisms or two different conditions of what we can have our measurements in, we need to be able to almost, correct or translate between the two. And in PP84, it is mentioned that, hey, if you got sealed condition, we can kind of relate the saturated resistivity to the sealed resistivity value using this kind of relationship dealing with the saturation and specifically a saturation coefficient. The documentation goes on to say, this coefficient, this M value, if you will, is been found to be between 3 and 5 in previous testing. And so, okay, that's great. We could potentially have a way to, reconcile this between the sealed and saturated states. However, we're not entirely sure if that 3 to 5 number applies to internally cured mixtures, because we have kind of another issue going on with that excess or additional porosity that's actually within the aggregate itself. And so when you have the lightweight aggregate, you have almost an order of magnitude higher porosity in that aggregate as you do normal aggregate, like a silica sand. And so that brings into question, all right, is that 3 to 5, or is that type of saturation coefficient, applicable to mixtures that have saturated lightweight aggregate? And then additionally, what might be the age effect, of this? And so that was kind of what we were going on to study. And unfortunately, this is more like a research in progress presentation. This is kind of where we're at right now, where we have more and more mixtures being made and tested, but you get one positive COVID test and it shuts down your lab for a couple weeks and everything. So we're going through this to determine really what would be an appropriate M value for internally cured mixtures with saturated fine lightweight aggregate. It may be between 3 and 5. It's just we don't know if that's the case or not, because there just really isn't that much data out there to systematically look at this. So that was kind of like the goal of this overall project. But then during the testing of all of this, we saw a bunch of blips in our data. Like if we look at this, our 28-day sealed, we see this in our 100% lightweight mixture. We don't see it in the others. And here's a zoomed in section. And remember, this line here is an average of 5 samples. And so we see this consistently sample to sample. And so we got this data and like, okay, we're obviously doing something wrong with the device. We probably selected the wrong setting or, just messed up something. And so, me not being an electrical engineer, I went upstairs in my building and there's an electrical engineer upstairs. He actually does research on the human body with the same exact equipment we're using and has the same exact issue. So when we have measurements and we have any chance of a residual impedance being present in our system, like we would if we had a bulk material like concrete or mortar and saturated coupling media like saturated sponge and steel plates, we have the potential to develop a residual impedance. And, outside of the civil engineering world and the bioelectrical world, this is a very well-known and studied phenomena. and in fact can be corrected. And so what is shown here is measurements taken, these are Bode plots, of using a impedance analyzer on a system that has some type of residual impedance. And we start, with the 0 ohm residual impedance, increase that. And we see when we get to relatively high residual impedance values, we start seeing a bunch of just what you might consider noise, spurious measurements in our system, because theoretically we should, in this example from this paper, should always measure 50 ohms. But when we start trying to measure our 50 ohm resistor, we're getting all this up here because we have this residual impedance present in our system. And we can see that in our raw data when we look at a Nyquist plot of this, of this right here. If we plot this on the Nyquist domain with resistance and reactance, we actually see this. These three curves here are kind of what we would expect. Actually, we wouldn't necessarily expect the second hump. That's another thing that we're dealing with. But we get this noise, and it's not good. And what's physically happening, the device, our impedance analyzer, can't actually balance the impedance because there's this residual effect present between our coupling medium and the bulk material. So talked to Todd. I was like, hey, can you tell us what we're doing wrong? He comes down, he looks at us, and he just laughs and says, oh, no, you're not doing it wrong. It's just a fact of your measurement system. Like, it is what it is. It's not that your device is malfunctioning. It's you have this built-in residual impedance. And so we're like, oh, okay. Well, let's look in the literature and see, has this been, talked about before, or, discovered? Or no, I shouldn't say discovered, just, discussed. And well, kind of. When you look at the literature and you're looking at, researchers that have previously done impedance analysis on cementitious materials, you occasionally will get them, plotting the Nyquist and Bode diagrams, but they never look like this. They never have this spurious measurement present. And so, that kind of led us to think, all right, well, maybe they're being extremely careful with how they're coupling their electrodes to their specimen. And so when we look at this publication in 1995 from Norway, we see that they actually discuss different coupling methods, including using metal meshes and brass meshes, embedded, not embedded, and so forth. And they settled on using a conductive graphite paint, if you will, to act as the coupling mechanism for the electrode. And that seemed to work really well. In this extensive study looking at bulk resistivity of concrete mixtures, they only used saturated sponges, but they took the sponges and measured the resistance of those sponges separately from the bulk material to kind of subtract out the effect of the actual residual or potential residual impedance from those sponges. And then finally, 30 years ago, what's really been setting this theory in place was looking at the actual phenomena in the system itself. And so if we plot on the Nyquist domain and we look at the actual data, we can generally separate out the bulk resistivity of just the concrete material itself from the resistivity effects of the electrode. And so this has kind of been, the driving force of how we're doing stuff. And we may, occasionally see this representative circuit present, describing what concrete with a, coupled system like saturated sponges or, even the graphite paint would look like. And, there's a phoretic piece right here that's kind of helping with the behavior of the electrode component. And when we look at this, okay, well, we have a circuit, we can, do math, we can do physics, electrical, theory on it. But we have a slight problem in that this circuit is not unique. In fact, if we took our data and tried to fit, a circuit to that data, we actually get several equivalent circuits. And so it's not a unique solution. And that kind of led us to, all right, we have an issue, well, not an issue, but we're seeing something with how we're coupling it. And it hasn't been, super well characterized in the literature. It's been mentioned, we could subtract resistivity of the sponges and so forth. And that, should work with a device that's only measuring at one frequency. But when we look at the spectra and we actually can evaluate the Nyquist behavior of this, that's where we actually start seeing some really interesting and, things that would lead us to want to look at this more. And so our future plan, well, we're going to complete this testing. We're going to run this impedance not only in the 2 electrode configuration, which is, top and bottom using the plates and saturated sponges. We can actually hook up our impedance analyzers to measure a 4 electrode configuration, which represents the surface resistivity measurements we could take. We're also going to very extensively evaluate this coupling medium. My electrical engineering colleague actually developed a printed circuit board that actually can switch and represent different residual impedances and all this, and that was part of that paper I showed earlier in the presentation. So we're going to look at that, and finally we're going to establish some recommendation for an M value that we can use to correlate between sealed and saturated lightweight internally cured mixtures in terms of their resistivity values. All right, and that's about it. Any questions?
You did great.
Yeah, I see a question here.
Okay.
Why do you think this effect shows only in certain mixtures? Well, we think that it has to do with the actual physical electrical properties of those mixtures. And, this study started out looking at lightweight aggregates. And when we see this spurious measurements in both the mixtures without lightweight and with it, that led us to think, okay, well, it may not just be the aggregates causing this. And so we started looking at the coupling medium and the sponges. And I didn't have enough data to show it, but very preliminary, what we've seen is even the brand of sponge can change this measurement, meaning some sponges you buy from the store have like this microban. It's a antibacterial, antifungal coating. And, if you take the sponge immediately out of the package and soak it in lime water or simulated pore solution and start taking measurements, you'll actually get a different reading than if you really rinsed out that sponge, before you used it. And, this is kind of addressed when in that paper that said, all right, we should measure the resistivity of these sponges separately. But the problem with measuring the sponges separately and then, measuring your concrete and subtracting out the 2 is if there's a possibility that residual impedance being there, that simple subtraction does not correct it. So we don't really have, a good answer on this so far, but based on what's been seen in the bioimpedance world, this is something that needs to be corrected a little bit more than just subtracting out the resistance of the sponge.